Good evening, dear students. Yes, so in the last class, we have started with the chapter Haloalkanes and Haloarenes. Okay, so what all things we have discussed in the last class? We have discussed the definition, okay, of haloalkanes and what are haloarenes. Okay, so the general formula of writing the haloalkanes and haloarenes. Okay, so these things we have discussed. Then we have discussed the classification of the halogen derivatives. Okay. So based on the number of halogen atoms present and the nature of the carbon to which the halogen is attached. Okay. So these were the things which we have discussed with examples. Okay. So we have seen what is allylic halides, what are vinylic halides, what are aryl halides, what are benzylic halides, right? Then we have discussed about the general methods of preparation of haloalkanes. So we have seen the main important preparations of the haloalkanes, that is group process. Okay, so as we have said that group process is important. So we prepare the haloalkanes from alcohol. So alcohols are the starting reactants. Okay, the starting reactant. So first, so we have also discussed what is a Lucas reagent. So what is Lucas reagent, students? Concentrated HCl plus and address ZnCl2. So we get the respective halo substituted alkene. Okay, that is a group process. Then we have seen the preparation of haloalkenes with the help of phosphorus trichlorides and phosphorus pentachlorides, right? So then the third important preparation from alcohol was with pyridine. Okay, we heat the thionyl chloride in the presence of pyridine. What we get? We get the chlorosubstituted product, and byproduct obtained is the sulfuric acid, that is sulfur dioxide, and pure hydrochloric acid. So this is another important reaction, that is Darson process. So Darson process is a very important process as the byproducts are the gases, and we know that gases escaped out easily, so we can easily collect our product. Then we have seen the free radical halogenation of alkanes. Okay, we have discussed about the free radical halogenation. Then we have discussed about the addition of hydrogen halides on alkene. So we have seen, so whenever we have an unsymmetrical alkene, so we have to follow the Markovnikov rule. So Markovnikov rules also we have discussed. So whenever we have to add a hydrogen halide, the negative part of the hydrogen halide will be added to the carbon with the least number of hydrogens, and the positive part, that is a hydrogen, will be added to the carbon with more number of hydrogens. Okay, so this is the Markovnikov rule. Anti-Markovnikov rule, it goes in the presence of a peroxide. So on the arrow, it is written as peroxide. That means it has to undergo anti-Markovnikov rule, which is reverse of Markovnikov rule. Then we have seen the addition of halogens across the triple bond. If we add halogen, we get a double bond and substituted halo products. If we add again a molecule of halogen across the double bond, we get a saturated compound. Okay, so this is about the addition of halogens. Then we have seen the halogen exchange methods, two important methods, that is Finkelstein's reaction and Schwarz reaction. Okay, what is Finkelstein's reaction and what is Schwarz reaction? So in Finkelstein reaction, we prepare iodoalkenes from alkyl chlorides and alkyl iodides, bromides in the presence of when it reacts with sodium iodide in the presence of acetone, we get what? Alkyl iodides. Okay. And Schwarz reaction is what? In Schwarz reaction, we get alkyl fluorides. Okay. So from the alkyl bromides or the alkyl chlorides, when they react it with metallic fluorides. Okay. Which are the metallic fluoride? We have taken example as HEF. So what we get? We get the respective fluorides substituted alkyl product plus AgBr. Okay, so this is very important halogen exchange method. And then we have discussed about the preparation of aryl halides by halogenation of aromatic hydrocarbon by side chain halogenation from benzene, diazonium salt, and from phenol. So these things we have discussed, right? So electrophilic substitution reaction, then by side chain halogenation. So halogenation, whenever we are doing halogenation, it goes in the presence of sunlight and one halogen. Okay. So till the hydrogen atoms are replaced. So at each step, hydrogen atoms are replaced with the halogen and we get the final product. Okay, halo substituted product. So next is from benzene diazonium salt. So we have discussed what is benzene diazonium salt. How do we get the benzene diazonium salt? So aniline, when so what are the starting reactant? Aniline, when it reacts with the sodium nitrate and concentrated HCl. Okay, you obtain what from concentrated HCl and sodium nitrate? You obtain nitrous acid. So nitrous acid, when it reacts with aniline, we get this benzene diazonium salt. So on benzene diazonium salt, so we get Sandwich reaction and Getterman's reaction. Okay. So respective chloro benzene and bromobenzenes are got. So please go through this. Then also we can, so we have seen the fourth one. Okay, this is not there in your syllabus. So we have seen this one that when you heat it with Ki, your benzene diazonium salt, we get iodobenzene plus N2 gas is liberated plus KCl. Okay, so these things we have discussed. I'm just revising. Okay. Then we discussed about the physical property of haloalkanes. So by boiling point, okay. Then the bond strength of haloalkanes, dipole moment, okay. And why the haloalkanes are not soluble in water? Okay. They are because they do not form any hydrogen bonding in water. Okay. And also we have discussed about the density of haloalkanes. Then today we are going to start with the chemical reactions. Okay, we are going to start with the chemical reactions of haloalkane. So this is also a very important part. Okay, asked for 3 marks. Okay, anyone question will be asked on the nucleophilic substitution reaction. Okay, so there are two nucleophilic substitution reaction. That is one is SN1 reaction. Second one is SN2 reaction. Okay, so what is happening in nucleophilic substitution reaction? So you can see that this is a alkyl halide. Okay, so this is alkyl halide. So as we know that, so also in the last class we have discussed that the alkyl halides, that is your RH. Okay, that is it is what? So this is a polar bond. Okay, I can take R can be your any suppose methyl ethyl okay, so I'll take CX bond. Okay, it is considered as CX bond, your alkyl group. So when you see the alkyl halide, so the CX bond, it is a polar bond. Okay, what it is? It is a polar bond. Yes. So we were discussing about the nucleophilic substitution reaction, that is our SN1 reaction. So as we have discussed that, so there is a alkyl halide group, which is represented as CX bond. So as we know that this CX bond is a polar bond. Why we say it is a polar bond? So there is a halogen atom, okay, which is attached. So this halogen atom is highly electronegative. So when an electronegative atom is attached, okay, so what will happen? The polarity will be developed. So it will tend to pull the electron towards itself. So as a result, the halogen will have a partial negative charge and your carbon will have a partial positive charge. Okay. So due to the minus I effect. So the your positively charged carbon, it will be easily attacked by your nucleophile. Okay. So and thus it will undergo what? And it will give you a and it will what it will do? It will substitute your nucleophile. Okay, that is your nucleophile will attack easily your positively charged carbon, and it will substitute your halogen. Okay, and you will get this nucleophilic substitution reaction. Okay, so the incoming nucleophile. So whenever the incoming nucleophile which we are using, it should be always stronger. Okay, than your leaving group. So this is called as a leaving group. Your X. Okay, it is a leaving group. So it leaves your and your nucleophile get attached to this positively charged and it forms this nucleophilic substituted product. Okay, so this is a nucleophilic substitution reaction. So these are the different examples of nucleophilic substitution reactions. Okay, so with different reagents, we are going to see the nucleophilic substitution reaction. So we have taken the starting reactant as what? Ethyl bromide. Okay, ethyl bromide. So when ethyl bromide, okay, when it with KOH, when you react it with KOH, what I'm going to get? I'm going to get, so your Br is the leaving group. Your Br is a leaving group, and in KOH, which is a nucleophile, it is OH minus. So your OH, okay, it will replace the Br and you're going to get ethyl alcohol. Okay, C2H5OH plus KBr is the product. So this is the substituted product. Okay, yes. So then same way with respect to second, the reagent is ammonia. Okay, so when we have ammonia, so what will be replaced? I am going to get what is my nucleophile? It will be NH2. Okay, NH2 minus. So your Br minus will be replaced by your NH2. I am going to get ethyl what? Ethylamine. Okay, I'm going to get ethylamine. Okay, then the next reagent is KCM. Okay, potassium cyanide. So when I have a potassium cyanide, my this is cyano group. My nucleophile is cyano group. So what I'm going to get? So my leaving group is Br minus. So Br minus will be replaced by Cn. So I'll get C2H5Cn plus KBr. Okay, so that is my substituted nucleophilic substituted product. Okay, then the next reagent is AgCN. Okay, AgCN, that is silver cyanide. Okay, silver cyanide. So here this AgCN, when it will react, okay, so what we can see that, so always your KCN. So whenever I have KCN, it will form the alkyl cyanides. Okay, it will form alkyl cyanides. And when you have AgCN, okay, AgCN, they form isocyanides. Okay, they form what? Isocyanide. So here it will be, the bonding is through Cn, and here the bonding is to N. Okay, nitrogen atom. So here your KCN is a ionic. Okay, so therefore your both carbon and nitrogen, they are free to link here. Okay, with the alkyl halide. But in case of your AgCN, okay, what will happen here? Then only nitrogen is available. Okay, so it will form what? Isocyanates. Okay, as the main product. Got it? Yes. So remember this. With KCN, I'm going to get alkyl cyanide. With AgCN, I'm going to get isocyanide. So this is isocyanide, NC. So my nucleophile will be NC. Next is potassium nitrate. Next is potassium nitrate. So potassium nitrate, my this is nitrito. Okay, nitrile group NO2 ONO. So my leaving group is Br. So it will be replaced. I'm going to get ethyl nitrite. Then silver, your silver nitrate. So my this is what? NO2. The nucleophile is NO2. So Br will be replaced by NO2. I'm going to get what? Nitroethane. Okay, I'm going to get nitroethane as a nucleophilic substituted product. Then your ethyl bromide, when it reacts with the alkoxide. Okay, so this is a sodium alkoxide. So when it reacts with sodium alkoxide, I'm going to get the ether. So when I have ROR dash linkage, it is called as what? It is called as the ether. So the functional group ROR dash, it is called as the ether formation. So when your alkyl halide, when they react with the sodium ethoxide, I'm going to get what? Ethyl ether. Okay, you can see the substituted ether. Then, so similarly, so the other substituted products are also formed. Okay. So these are the main important. So please remember about KCN and AgCN. When KCN reacts, it will form cyanides. Okay, alkyl cyanides. And when AgCN reacts, it will form isocyanides. Okay, very important. Yes. So these were the things which we have discussed. Okay. Okay. So the main important nucleophilic substitution reactions are of two types. Firstly, the SN1 reaction, that is called as the unimolecular nucleophilic reaction. And the second one is SN2 reaction, that is a bimolecular nucleophilic reaction. Now, what do you mean by SN1 reaction, students? Okay, so that is a unimolecular nucleophilic substitution reaction. So the rate of the reaction, it depends upon only one substrate. Okay, on the one substrate. Okay, so the rate of the reaction, it depends on only one substrate. So it is a unimolecular. Okay, it is a unimolecular. Now here, the SN1 reaction, it occurs. So what things you have to remember? It occurs to two steps. Okay, it occurs to two steps. So it is a unimolecular. It is a unimolecular reaction. Okay, the rate of the reaction, it is a first order kinetics. It depends on what? It depends on the first order kinetics. Okay, so the rate of the reaction depends on concentration of only one this okay alkyl halides. It depends upon the concentration of only one alkyl halide. Now here, so the rate of the reaction it undergoes by a two-step. Okay, the reaction undergoes two-step. So the first step is what? So you have a alkyl halide. So tertiary alkyl halide is there. Okay, tertiary alkyl halide is there. So this tertiary alkyl halide, so what will happen? The first step is a slow step. Okay, first step is a slow step. So what will happen here? So the polarization, as we know that the CX bond is a highly polar. So what will happen? There will be the halogen will tend to pull the electron towards itself. So as a result, there will be partial negative, partial positive charge, and it will the bond, and what will happen? The halogen will take its electron with it and it will leave. Okay, so the carbon will be left with a positive charge. So this is the first step. Okay, this is the first step. So formation of carbocation. What is that? Formation of carbocation. The leaving group will leave with its pair of electrons. Okay. Then the next step is what? Next step is attack of a nucleophile. Okay, attack of nucleophile. So attack of nucleophile. So how the attack takes place? So whatever the this is formed here. What? Okay, whatever the carbocation is formed. So there is a nucleophile. So okay, if I use a KOH, okay, so nucleophile, what will do? It will attack the positively charged carbon. So this reaction is very fast. Okay, this reaction is very fast, and I'm going to get a substituted alcohol. Okay, product. So tertiary alcohol I have got here. So these are the two steps. First one is what? Formation of carbocation. Formation of carbocation. And the second step is attack of nucleophile. Okay, attack of nucleophile. So step one, and this is step two. Okay, attack of nucleophile. Is it clear? So very, very important, 3 marks question. So you should remember that SN1 reaction, it follows the first order kinetics because the rate of the reaction depends upon the concentration of only the alkyl halide. Okay, and does not depend on the concentration of the nucleophile. It depends upon the concentration of only nucleophile. That is your alkyl halide. Okay, so it depends only on the concentration of alkyl halide. So it follows the first order kinetic. It goes via two steps. First step is a slow step where a formation of carbocation takes place. Okay, and the second step is a fast step where the attack of nucleophile takes place. Okay, so these things you have to remember. Okay, is it clear? Okay. So you have to remember that the reactions, yeah, SN1 reactions, they are followed by the polar protic solvents. Okay, they undergo the SN1 reaction in the presence of polar protic solvents like your alcohol, water, okay, or organic any solvents. Okay. So, and the stability. So we have seen the carbocation. So the stability of carbocation will be more, okay, the rate of reaction, greater the stability of the carbocation, more will be the rate of reaction. Okay, so when we say the order of stability, so tertiary carbocations are more stable, then secondary, then primary, and then your methyl cation. Okay, so these things you have to remember. Okay, is it clear? So tertiary are more stable, then secondary, then primary, and then methyl carbocation. So this is the stability of the carbocation. So SN1 reaction, very important. Okay. Please study the SN1 reaction properly. So carbocation and all, you have to write it properly, stepwise. Okay. So rate of the reaction depends on only the concentration of the alkyl halide. Yes. So it is a first order reaction. The reaction order of alkyl halide towards the SN1 is tertiary carbocation is more stable, then secondary, and then the primary. Polar solvents, low concentration of nucleophiles and weak nucleophiles favor the SN1 mechanism. So polar solvents are used. Okay, in the presence of polar solvent only SN1 reactions are carried out. And in SN1 reaction, partial racemization occurs due to the possibility of frontal as well as backward attack or planar carbon. Racemization means you will get 50% retention and 50% inversion. So that is called as the racemization. So it is the chances are there that there will be racemization. So attack can take place from both the side. Okay, the attack can take place of the in the second step. Okay, in the second step, the attack can take place from the this side also, or it can take place on the this side also. Okay, so that is called as the possibility. Okay, racemization. So racemization means the attack can be from the front side also, it can be from the behind also. So these are the some of the features, okay, of the SN1 reaction. Next, so this is the what I had discussed about the racemic mixture. Okay, so from the back side, if the takes place from the back side, okay, and this is the attack which is taking from the front side. So if the attack takes place from back side, this is a product which is formed, okay, and if the attack takes place from the front, okay, then this is the product which is formed. So this is called as racemic mixture, 50%, okay, and this is 50%. So that is racemic mixture. So we are going to discuss about stereochemistry in the front slides. Okay. Next, we are going to see the SN2 type. Okay. What do you mean by SN2? Bimolecular. So by the word bimolecular, what you will understand? Yes, by the word bimolecular, what you will understand? So bimolecular means the rate of the reaction depends on the concentration of the alkyl halides and also on the nucleophile. Okay, so here in this reactions, the rate of the reaction depends on both the that is the concentration of the alkyl halide and also on the nucleophile. Okay, and in this, so that is your, so what it follows the second order kinetics. It follows the second order kinetics. Okay, and it undergoes via one step. Okay, it undergoes via one step. Okay, it will undergo via one step. Okay, so in SN1, SN2 mechanism, so it will undergo through a inversion of configuration. It will undergo via inversion of configuration, and that is called as the Walden configuration. Remember this word? What is that? It is a Walden inversion. Okay, so in SN2 mechanism, inversion of configuration occurs, and that inversion of configuration is called as the Walden inversions. Okay, so what do you mean by that? Okay, now suppose, so this is CH3Br. Okay, CH3Br. So this is CH3Br. So what will happen here? What will happen here? So this is a methyl bromide. So this is your what? Your this what? Nucleophile. So now the nucleophile attack will takes place from back side. So what will happen here? So it will undergo a inversion of configuration. What it will undergo? Inversion of configuration. So what will happen here? So breaking of bond and making of bond takes place simultaneously. So this is called as a transition state. What it is called as transition state. Okay, and what I'm going to get? I'm going to get a inverted product. What I'm going to get? I'm going to get a inverted product. Okay, I'm going to get a inverted product. So this is called as Walden inversion. You can see inverted means what? See how this is and how the product is formed, right? So it is ulta, right? So it is reverse of that. So this is called as inversion. So what is happening here? So the attack of the nucleophile takes place from behind. So as a result, what will happen? So the new bond is forming here and the old bond is breaking here. Okay, it is breaking and this is making. So making and breaking of bond takes simultaneously and it undergoes via a transition state to form a new inverted product. Okay, so this is what your the SN2 mechanism. So the rate of the reaction depends on both the alkyl halide as well as the nucleophile. Okay, so this is the SN2 type. So this is called as SN2. Okay, SN2 nucleophilic substitution reaction. So I hope this is clear. What is the SN1 mechanism and SN2 mechanism? So when we see the stability here, okay, when we see the stability of the your your alkyl halides in SN2 mechanism. Methyl carbocation is the most stable, then your primary carbocation, then secondary, then tertiary. Okay, so why? What is the reason? Due to steric hindrance. So if I take here the tertiary carbocation, so if I take here tertiary carbocation, so these CH3, so again CH3. Okay, and CH3. So this is my tertiary carbocation. Okay, and if I see, this is a methyl carbocation. Okay, so when the attack of now, if I want to attack the nucleophile, if I want to attack the nucleophile, so here, so much steric hindrance is there, right? Big molecules are present. So it is very difficult for the nucleophile to attack the carbon. But here in case of the your methyl carbocation, so easily the attack is possible. Okay, so the reason is due to steric hindrance. Okay, so due to steric hindrance, okay, so methyl carbocations are more stable, then primary, then secondary and tertiary. I hope this is clear. Yes, is it clear? Okay, fine. So remember that the substitution nucleophilic bimolecular reaction, it follows second order kinetics and the rate of the reaction depends on the concentration of both alkyl halide and nucleophile. Okay. Yes. Let us go for the next one. So this is the Walden inversion. Okay. What I have explained you. So the nucleophile attacks from the behind. Okay. To the your alkyl halide. So what is happening? The new bond is forming, the old bond is breaking, and what you can see, it will undergo a transition state. Okay, so a new bond making and breaking of bond takes place simultaneously and you get an inverted product, which is called as the Walden inversion. Okay, yes. So very important, both SN1 and SN2 are both important. So reactivity of halides towards the SN2, primary alkyl halides is more stable, then secondary and then tertiary. The rate of the reaction in SN2 depends on the strength of the attacking nucleophile and the alkyl halides. Okay. Then strength of some of the common nucleophiles. So cyanides are more, then your iodides, then OR minus hydroxyl, then your water and fluorides. So for the SN2 mechanism to undergo, so we require non-polar solvents, strong nucleophiles and high concentration of nucleophiles. Okay, so they will favor the SN2 mechanism. So these are some of the features of SN2 mechanism. So so next we are going to start the stereochemical aspects. Okay, let us see the stereochemical aspects of nucleophilic substitution reaction. So the first important thing which you have to understand about the stereochemical aspect is what is a plane polarized light. Okay, so first let us understand the plane polarized light. So you can see the bulb. Okay, so here you can see a bulb. So whenever a bulb, okay, or a beam of light, when it falls from this bulb, so it consists of what? It consists of the waves. Okay, it consists of the ordinary light, and these ordinary light, what they do, they consist of what? They, this ordinary light, it consists of the waves, and these waves, what they do, they vibrate in all the direction. Okay, they vibrate in all the direction. Now this beam of light, okay, which is fallen from this bulb, okay, which is consisting of the waves which are vibrating in all the direction, it is passed through a nickel prism. Okay, nickel prism, it is a polarizing filter. Okay, you can say it is a polarizing filter. So what it will do with the light waves which are vibrating in all the direction, it makes them plane polarized. It will make them travel in only one form. Okay, in a polarized plane. So this is called as the plane polarized light. So how we get the plane polarized light? So when a beam of ordinary light, which is consisting of the waves which are vibrating in all the direction, okay, when it is passed to the nickel prism, it becomes a plane polarized light. So they are made to vibrate in only one direction. Okay, so this is your plane polarized light. Okay, is it clear? Yes, okay. Next is the optical isomerism. Next, we are going to start with the optical isomerism. So what do you mean by optical isomerism? So the compounds having same molecular formula and structure formula, but where they differ in the direction of rotation of plane polarized light. Okay, where they differ in the direction of plane polarized light. Then they are called as the optical isomers, and the phenomena is called as optical isomerism. So if the plane polarized light is rotated to right hand side, then it is a plus lactic acid. Okay, then we give it as plus lactic acid. So if the plane polarized light, it is what? It is rotating in the right side. Then it is it gives rise to lactic acid plus lactic acid. When the plane polarized light is moving to the left hand side, okay, then it is called as the minus lactic acid. Okay, so the compounds having same molecular formula and structure formula, where they differ in the direction of the rotation of plane polarized line. Okay. Next important concept is chiral center or the asymmetric center. Okay, chiral center or the asymmetric center. So suppose I have a carbon atom. Okay. Around the central carbon atom, there are four different groups. Okay, which are arranged in a tetrahedral form. Which are arranged in what? Which are arranged in a tetrahedral form. Okay. So here, if the four atoms which are attached to the central carbon are different, okay, if the four atoms which are attached to the central carbon are different, then they are called as the chiral carbon, or it is called as the asymmetric center, or it is called as the stereo center. Understood? This carbon center is called as what? It is called as the chiral center or the asymmetric center or the stereo center. When it is called, when you are arranging four different groups. Okay, all the groups are different around the central carbon atom. Okay, if the substitution attached to that carbon is different, then what we say, then such a carbon is called as the chiral center or the symmetric center or the stereo center. So what all things we have discussed? We have discussed about the plane polarized light. We have discussed what is optical isomerism, and we have discussed about the chiral center or the asymmetric center. So these things which we are applying here. Okay. Next is, what do you mean by chirality? Next is, the word comes is chirality. Now, what do you mean by the word chirality? So whenever I have a object, okay, I have a object or a molecule. Now, suppose I have now this your palm. Okay, so this palm, what it will do, an object or a molecule. So if I put the mirror, if I take the mirror image of this, and so this is the mirror image of this palm. So what I'll do now, I'll put one on the above. So is it superimposable? No. Okay. So an object or a molecule which is not superimposable on its mirror image, it is called as the chiral. And this property is called as what? It is called as the chirality. Okay. So take your palm. Okay. To take your palm like this. And what you do? Take the mirror image of that. So if I take the mirror image of that, okay, now what I'll do? I am not going to put this on this. Okay, your thumb is your, this is your little finger. Now this is your little finger, this is your thumb. Okay, so when you put this on this, your mirror image on this, it is not superimposable. Okay, it will not fall one on one. Right, so then that is called as the chiral and the property is known as the chirality. Okay, so remember this. What is chirality? So a molecule or object which is not superimposable on its mirror image is called as the chiral and the property is called as the chirality. So, and what do you mean by achiral? It is opposite. Okay, what do you mean by achiral? Achiral means it will the superimposable mirror image. Okay, it will be the object or a molecule will have the which are superimposable on their mirror image. They are called as a achiral carbon. What they are called as achiral carbon. So the object or a molecule which are superimposable on their mirror image. Okay, they are called as the achiral molecule. What they are called? Achiral molecule. Okay. Next is the enantiomers. Next is the enantiomers. So what do you mean by enantiomers? So stereoisomers which are non-superimposable on their mirror images are called as the enantiomer. Now you can see the molecule. Okay, so this is a S-aniline. So you can see this is a COH group, CH3 group, H and NH2. So four different groups. So this is a chiral carbon. Okay, this is a chiral center or the chiral carbon. So these are the stereoisomers which are non-superimposable. So what they have done, they have taken the mirror image. Now if I put this on this, okay, so the CH3 will come here, but here it is hydrogen. Here the hydrogen is there, but here it is CH3. So the mirror images, they are not superimposable on their mirror images. Okay, the stereoisomers, they are not superimposable on their mirror image. Then they are called as what? Enantiomers. Very important. So they will ask you question, what are enantiomers? Give an example. Okay, so very important. Next is racemic mixture. So already we have discussed about racemization. Okay, so you have both the products will be 50-50. So either the attack will take place from front or it will take from behind. So you are going to get, so it is a equimolar mixture of dextro and levorotatory. Okay, so when you have 50% dextro rotatory and when you have 50% levorotatory, then what will happen? Then this is called as the racemic mixture or the racemic modification. So 50-50, what will happen? One, it will be zero optical rotation. Okay, so one isomer will balance the other. It will cancel out, right? It will cancel out. So racemic mixture. So 50% dextro, 50% levo. It is called as the racemic mixture. So it has a zero optical rotation. It has a zero optical rotation, so it will cancel one another. Okay, so it is a racemic mixture. So these all definitions you need to know. Okay, yes. Next is the meso compounds. Next is the meso compound. So what do you mean by meso compound, students? So meso compounds, they are the optically inactive. Okay, meso compounds, they are optically inactive due to the presence of plane of symmetry in the molecule. Now, what do you mean by plane of symmetry? So I have a molecule here. Okay, I have a molecule. So HOH, HOH, and COH. So if I put a mirror here, so what you can see, this half molecule is same as this half molecule. So it will cancel each other. So what will it will happen? It will optically be inactive. It is a optically inactive. Why it is optically inactive? Because this will cancel each other due to the presence of symmetry in the molecule. So meso compounds, what do you mean by meso compounds? They are optically inactive. Okay, they are optically inactive due to the presence of plane of symmetry in the molecule. So you have to remember the examples. So they can ask you what are meso compounds? Give an example. Okay. So why meso compounds are optically inactive? Why? Because the presence of plane of symmetry. Okay. So next we are going to discuss about the elimination reaction. Next we are going to discuss about what? The elimination reaction. So elimination reaction. So the that is a dehydrohalogenation. So what do you mean by dehydrohalogenation, students? So hydro means one hydrogen. D means removal. Okay, D. Whenever you have a word D, okay, D means removal of hydro is hydrogen and halo is halogen. Okay, your X can be your Br, Cl, etc. So removal of hydrogen halide. Okay, it is a beta elimination reaction in which halogen is form is from alpha carbon atom and the hydrogen is from the alpha carbon according to Setzeff rule. Okay, according to Setzeff rule. Okay, show you. Let me show you this. So I'll take an example. So I have taken an example here. So I have CH3. Okay, I have CH2. Then this is CHBr and this is CH3. Okay, so this is a molecule. Let me write this CH3 also like this only. So CH, H and H. So this is the same molecule I have written. Okay, complete structure I have written. Now here, what is happening here? Okay, what we are going to do? So I am going to remove one hydrogen and one halide. So one hydrogen and one halide is removed. Okay. So one hydrogen and one halide is removed. So what I'm going to so how this dehydrohalogenation reactions, they are also called as a beta elimination reaction. It undergoes in the presence of alcoholic KOH. So there can be a question: what is the which is the dehydrohalogenating agent? Which is a dehydrohalogenating agent? It is alcoholic KOH. Okay, alcoholic KOH is used as a beta elimination reaction or it is used as a dehydrohalogenating agent. So what it is doing, it is removing one hydrogen and one halide. So you can see here, so what will happen, one hydrogen from here and one halogen from here is removed. So what I'm going to get, so I'm going to get CH3, okay, then C, then I'm going to H, double bond CH and CH3. Okay, so this is the product. Okay, this is the product. So this is a major product, okay, which I am going to get. So the ease of dehydrohalogenation among the halide tertiary is more stable than secondary and then the primary. Okay. So beta elimination reaction, it occurs, okay, from the alpha carbon atom. Okay. So in which the halogen is from the alpha carbon atom and the hydrogen is from the alpha carbon according to the Setzeff rule. So this is a following the Setzeff rule. Okay, it is following the Setzeff rule. So elimination reactions, very important reaction. Next is the reaction with metals. So again, very important. So name reactions, three name reaction. The first one is the Woods reaction. So mark this as important, student. Mark these as important. So first one is a Woods reaction. So in Woods reaction, 2 moles of alkyl halides, okay, 2 moles of alkyl halides, when they react it with sodium, when they react it with sodium, okay, 2 moles of alkyl halides, when they react it with sodium, okay, so this is another molecule of alkyl halide. So this is one, this is another. In the presence of sodium and dry ether, so the solvent taken is dry ether, I'm going to get what? So I'm going to get a higher alkane plus 2NaX. Okay, so this is the Woods reaction. This is the Woods reaction. So I'm going to get a higher alkane. Okay, I'm going to get a higher alkane and NaX. So this is Woods reaction. Then what is a Wood-Fittig reaction? Now in Woods reaction, we have taken 2 alkyl halides. Okay, in Wood-Fittig reaction, I'm going to take one alkyl halide. Okay, same in the presence of sodium and one will be my this what I'm going to take one benzene ring. Okay, aryl halide. I'm going to take a aryl halide. So again, same, it will undergo in the presence of dry ether. What I'm going to get? What I'm going to get, students? Yes, what I'm going to get? So this is my product plus 2NaX. Okay, so I'm going to get a substituted product. Okay, so that is a aryl alkyl substituted product. Now here, let me give you one examples now. One example. So let me take here RsC2H5. Okay, let me take and XsCl plus 2Na plus 2Na plus Cl and C2H5 in the presence of dry ether. What I'm going to get, students? What I'm going to get? I'm going to get a what I'm going to get? I'm going to get a butane plus 2NaCl. Okay. Similarly, here I'll write R, I'll take it as CH3. This I'll take it Br plus 2Na plus Br, and this is your benzene. What I'm going to get in the presence of dry ether, students? I'm going to get a CH3 and benzene plus 2NaBr. Okay, so I got a toluene. So this is a second Wurtz-Fittig reaction. So one alkyl halide and one aryl halide. I hope this is clear. Okay. Next is a reaction with Mg. So when you are alkyl halide, okay, when you are alkyl halide, so here they have taken as ethyl bromide. So I have taken a ethyl bromide. So ethyl bromide, when it reacts with magnesium, when it reacts with magnesium in the presence of dry ether, I am going to get a organometallic compound which is called as a Grignard reagent. What it is called as Grignard's reagent. Okay, so ethyl bromide. So reaction with Mg. So that is your ethyl bromide when it reacts with a metal, active metal like magnesium in the presence of dry ether. I am going to get a organometallic compound. Okay, I am going to get a organometallic compound. So this is the RMgX, that is your Grignard reagent. Okay, is it clear? These all three reactions with metals are important. Okay, all these reactions with metals are very, very important. Is it clear, students? Okay. Okay. Let us go for the next one. So next we are going to discuss the physical properties of aryl halides. Okay, next we are going to discuss the physical properties of aryl halides. So aryl halides, they are the colorless liquids or the colorless solids, and they have some characteristic order. Okay, they have some smell. They have the some particular smell they have. Okay, then boiling point. What happens to boiling point of this aryl halides? They generally increase. Okay, because there is an increase in the size of the aryl group or the halogen atom. So boiling point also increases. So this is the boiling point order given. Then the melting point of para isomer is more than the ortho and meta isomer. Why? Because so what do you mean by para, ortho, and this? So this is a para product. Okay, this is a para. Okay, and this is a ortho. Okay, and this is a meta. So what do you say now? So they say that what it is, the melting point of para is more than the ortho and the meta. What is the reason? They say that is due to symmetry. So here you can see if I put a plane of symmetry here, okay, if I put a plane of symmetry, okay, so it is same. Now here there is no plane of symmetry, right? So because of that more symmetrical nature of para isomer, it is having more boiling point, melting. Okay, then your ortho and meta. Then due to the resonance in chlorobenzene, CCl bond is shorter and hence its dipole moment is less than the cyclohexyl chloride. Okay. Next, we are going to discuss with the chemical properties of aryl halides. Okay. Next, we are going to discuss with the chemical properties of aryl halides. Okay. So let us discuss. The first one is the nucleophilic substitution reaction. First one is the nucleophilic substitution reaction. Second one is the electrophilic substitution reaction. Third one is the reaction with metals. Okay, so these are the chemical properties. So aryl halides, as we know, the aryl halides. So how do we represent the aryl halides? So these are the aryl halides. So these aryl halides, they are less reactive. Okay, they are less reactive towards the nucleophilic substitution reaction. So because of their low reactivity. Okay, their low reactivity is attributed because your benzene is also highly, what? It is highly nucleophilic in nature. So how come the nucleophile will attack another nucleophile, right? So because there is a low reactivity is attributed, and there are following reasons. So first reason is what? The CX bond has a partial double bond character. This your CX bond. Okay, it will have a partial double bond character is seen in your aryl halide. So whenever you see the aryl halide, so there is a partial double bond character is observed. Okay, and then is the stabilization of molecule. So the stabilization of molecule will occur. So if I write the Cl bond like this, okay. So what will happen? So this will undergo the resonance. Okay, it will undergo the resonance, and what I'm going to get? So I'm going to get a negative charge here. So when I write this Cl, okay, so this will get a positive. So you can see that here, what is you can see that the CX bond. So this is a CX bond, and this CX bond, okay, is having a partial double bond character. And the stabilization of molecule by delocalization of electron. So the stabilization of the molecule is by the what we are doing? We are doing the delocalization of electron. Delocalization of electron means what? Movement of electron, and there is a instability of phenyl carbocation. Okay, so in instability. So in haloarenes, the phenyl carbocation, okay, which is formed as a result of self ionization. Okay, it will not be stabilized by resonance. So the phenyl carbocation cannot be stabilized by resonance. Okay. So SN1 mechanism is also ruled out there. So these are the why aryl halides are less reactive. So the question is there. So there can be a question why it is less reactive towards a nucleophilic substitution reaction. So you have to explain the following points. Next, however, the aryl halides they have electron withdrawing groups like NO2, SO3H at ortho and para positions undergo nucleophilic substitution reaction easily. So here, okay, so aryl halides, when they have an electron donating withdrawing group, okay, when you have such electron withdrawing group, so it will undergo nucleophilic substitution easily. So now I have a chlorobenzene. So I have a chlorobenzene. Now this chlorobenzene, okay, what I have done, I have reacted with NaOH at 623 Kelvin and 300 atmospheric pressure, followed by acid hydrolysis. I got a phenol. I got a phenol. Okay. So these are the reactions. So these are the reactions. So chlorobenzene. So what is happening here? We are replacing the halogen by a hydroxyl group. Okay, so we are converting the haloarene into a phenol. So by heating it with heating at high temperature, okay, 623 Kelvin and 300 atmospheric pressure, okay, with NaOH followed by acid hydrolysis. So what I'm going to get? So first I'm going to get a sodium phenoxide and followed by acid hydrolysis. So your Na will be replaced by H. Okay, I'm going to get phenol. Right. Next, presence of electron withdrawing group increases the reactivity. So just now we have seen, so there is an electron withdrawing group. So whenever electron withdrawing group, the reactivity increases. Okay, so nucleophilic it takes place. So you can you hear me? Yes. Okay, so let us continue. So here, so where we were, yes. So electron, the presence of the electron withdrawing group, what it will do, it will increase the reactivity. So which electron group is there? Withdrawing group, NO2 is there. So what we have done NaOH, we are reacted with NaOH at 443 Kelvin followed by acid hydrolysis. We get the what? So the whenever you have the electron withdrawing group, okay, at ortho and para position, what it will do, it will increase the reactivity. So I got a ortho substituted product here. Okay, so I got nitrophenol. Okay, orthonitrophenol. Then here we can see that is there is a trinitrophenol. Okay, trinitrobenzene is there, chlorobenzene. So I am warming it with water. What I am got? So your Cl is replaced by OH. Okay, So another nucleophilic substitution reaction. Then let us see the electrophilic substitution reaction. Okay, so halogens, they are deactivating. So they are said to be deactivating, but ortho para directing. So halogens, they are deactivating groups, but they always try to attack the ortho and para position. So we can do chlorination, nitration, sulfonation, and Friedel-Crafts reactions, and it will give you a mixture of ortho and chloro substituted product. So let us see the electrophilic substitution reactions on the haloarenes. So this is your chlorobenzene. Okay, this is your chlorobenzene. When you react it with Cl2, okay, when you react it with Cl2, okay, that is your halogen, in the presence of a catalyst like anhydrous FeCl3, okay, I got 1,4-dichlorobenzene. I got 1,4-dichlorobenzene. So this is a para substituted benzene. And here I got a ortho substituted benzene. So whenever or para substituted products are stable as compared to the ortho. So very important, any electrophilic substitution is asked. Okay, so this is a halogenation reaction. Next is nitration. So how the nitration is carried out? So our starting, this is chlorobenzene. So chlorobenzene, we are taking the nitrating mixture. What is our nitrating mixture? Concentrated HNO3 plus concentrated H2SO4. Okay, concentrated HNO3 plus concentrated H2SO4. They are called as the nitrating mixture. Which is the electrophile? It is NO2 plus. Okay, it is NO2 plus. So our electrophile will attack the ortho and para position. So the para position is more stable as compared to the ortho. So this is the nitration reaction. Okay, or the electrophilic substitution reactions are very important. Next is sulfonation. Next is sulfonation. So chlorobenzene, when we react it with concentrated H2SO4, okay, so which is our H3, okay, so this is our HSO3H, okay, SSO3H plus. So this is our your electrophile. Okay, so that will attack your ortho and para position. So this is sulfonation. Sulfonation is carried out in the presence of concentrated H2SO4. You are going to heat the chlorobenzene and you get ortho and para substituted product. Is it clear? Okay. So next is the Friedel-Crafts reaction. Okay, next is the Friedel-Crafts reaction. So Friedel-Crafts reaction, they take place by two. One is the Friedel-Crafts alkylation and next is the Friedel-Crafts acylation. So this is Friedel-Crafts alkylation and this is Friedel-Crafts acylation. Okay, so this is the alkyl group. This is the acyl group. So it takes place in the presence of the catalyst like anhydrous AlCl3. Okay, so here, which is the electrophile, okay, if I take CH3Cl, our alkyl group, that is CH3 plus is the electrophile. So it will attack the ortho and para position. So para positions, ortho para substituted products are more stable. Okay, so this is the major product. So similarly, when you have a acyl group, so my R is here CH3, C double bond O Cl. So this group will go and attack. So what I got? COCH3 will attack. Okay, so COCH3. So CH3, C double bond O is the electrophile. Okay, so I will get a ortho and para substituted product. So again, the para is more stable. So both the products are obtained, but more stable will be the para product. Okay, so this is the Friedel-Crafts reaction. Next is the reaction with metal. So we have seen what is Woods reaction. We have seen what is fatigue reaction. Okay, so this is the Woods fatigue reaction. So we are going to take one aryl halide, one alkyl halide in the presence of ether and sodium. We get a what? Alkyl aryl. Okay, substituted product plus NaX. So this is a Wood fatigue reaction. Then what is a fatigue reaction? Fatigue reaction means what? We have to take both aryl halides. Okay, both aryl halides are there. Okay, both aryl halides are there plus 2Na plus, so like this. Okay, plus X. So this is your, so what I'm going to get in the presence of dry ether again, I'm going to get a diphenyl. What I'm going to get? I'm going to get a diphenyl plus 2NaX plus 2NaX. Okay. So this is my Fittig reaction. So Wood's reaction, it takes place, okay, in the presence of two alkyl halides. Okay, alkyl halides, two molecules of alkyl halides reacted with sodium in the presence of dry ether. I get what? Higher alkanes. When a Fittig reaction means both are aryl halides. Okay, aryl halides in the presence of sodium and dry ether, I'm going to get what? Diphenyl. Okay. And when what is Wood-Fittig reaction? One alkyl halide and one aryl halides. Okay. So that is your Wood-Fittig reaction. Okay. So next we are going to see some dihalogen derivatives. Okay. Next is the dihalogen derivatives. So there is a dihalogen derivatives, that is dichloromethane. Okay, dichloromethane, that is CH2Cl2. It is used as a solvent. Okay, that is as a propellant in aerosol. So a direct contact of dichloromethane in human causes intense burning and milk redness of the skin. So if you come direct in contact with this dichloromethane, it is very dangerous. Okay, it causes intense burning and there will be redness. Okay, in the skin. So you have to know the uses of the dihalogen compounds. Next is the trihalogen derivatives. So first one is the chloroform. Okay, often you have come across this chloroform in the lab. Chloroform, it is called as a trichloromethane. Okay, it is called as a trichloromethane. So how we are going to prepare that? So methane, okay, we have to do chlorination in the presence of sunlight. I'm going to get trichloromethane. So all the hydrogens of the methane is continuously, okay, when you are doing controlled chlorination, at each step the hydrogen is being replaced by the chlorine. Okay, so I am going to get a trichloromethane. So by haloform reaction also, you can prepare the chloroform. So these are the two methods of preparation. So what are the properties of this chloroform? So oxidation of chloroform, it gives you a poisonous gas, which is known as the phosgene. Okay, that is COCl2. Very important. Mark this as important. Okay, question asked. That is oxidation of chloroform. That is your CHCl3. Which gas is released? Okay, which gas is given out? Which poisonous gas it is? It is a phosgene gas, and what it is called as carbonyl chloride. Okay, so please remember the equation. So CHCl3, we are doing oxidation in the presence of light. What I'm going to get? COCl2 plus 2 HCl. So this is phosgene. Okay, so this is phosgene. Okay, so to avoid this oxidation of chloroform, okay, we have to keep it in the dark bottles, dark brown bottles. So we have seen in the laboratories how the chloroform is kept. It is kept in the dark brown bottle so that it will not come in contact with the light. Okay, so if it comes in contact with the light, it will start giving out the poisonous gas. And where this chloroform is used, it is used in the production of freon refrigerator. So very important. They'll ask you where the chloroform is used. It is used in the freon refrigerant R22. Okay, so remember this. So these are the properties of your chloroform. Okay. So next is the polyhalogen derivatives. So polyhalogen derivatives, that is carbon tetrachlorides, freons, DDT, and perchloroethane. Okay. Now, how do you get this carbon tetrachloride? So again, controlled oxidation. Okay, controlled your chlorination in the presence of sunlight. You are going to get the carbon tetrachloride. Okay. So carbon tetrachloride, it is a colorless, non-inflammable, poisonous liquid. It is soluble in alcohol and ether. So where it is used, okay, it is used as a solvent for oils, fats, resins. It is used in dry cleaning and it is used as a fire extinguisher. Okay. So freons. Next important concept is freons. So what are these freons? The chlorofluorocarbons. Okay, they are called as a CFCs. So the chlorofluorocarbons or compounds of methanes and ethane, they are collectively called as what? They are collectively called as the freons. So very important. They'll ask you the question, what are freons? Okay, what are freons? The chlorofluorocarbon compounds of methane and ethane. They are collectively known as what? They are collectively known as the freons. Okay, so where they are used, usually they are produced for aerosol propellants in refrigeration and air conditioning purposes. Okay, so this is the freons. Okay, so remember how the freons are prepared, how they are produced. Okay, next is DDT. So in DDT, what is important is you need to know the structure of DDT. Very important. Okay, one more question. Structure of DDT. So and the name, it is a dichloro diphenyl trichloroethane. So what is the DDT full form and the structure you need to know. Dichloro diphenyl trichloroethane. So it is the first chlorinated organic insecticides. Okay, and it is prepared from chloral and chlorobenzene in the presence of concentrated H2SO4. Okay, so what you need to remember how it is prepared, okay, and what is the full form and the structure of DDT. Okay. Yes. So this completes your chapter, haloalkanes and haloarenes. Okay. So in this chapter, haloalkanes and haloarenes, so we have discussed the complete this. Okay. That is, we have discussed about the definitions. Okay. We have seen the classification. Also, we have discussed about the general methods of preparation of both alkyl halides and aryl halides. Okay. Then we have discussed about the physical properties of alkyl halides and the physical properties of aryl halides. Also, we have discussed about the chemical properties, chemical reactions of alkyl halides and chemical reactions of aryl halides. Okay, nucleophilic substitution reactions, different nucleophilic substitution reactions, the two types SN1 and SN2. Then we have also studied about the stereochemical aspects, okay, which are involved. Okay, then we have discussed about the elimination reactions, then some of the reactions with metals, okay, so and the electrophilic substitution reactions, and lastly the dihalogen derivative. So these are some of the important things which we have covered from this particular chapter. Okay, so this completes your chapter haloalkenes and haloarenes. So in the further classes, we are going to, in the next class, we are going to discuss about the next chapter, that is alcohol, phenols and ethers. I hope you have understood. Yes, fine. So I shall end this session here. So we'll meet in the next class. Thank you.